So now we have Javier Goicoechea from CSIC, Madrid, telling us everything about physics and chemistry of the interstellar medium.
So thank you very much. Thank you to the organizers for giving me the opportunity to talk to you at the end of the afternoon. I hope to do it well. I didn't want to be pretentious with this title. You know, obviously I will talk about some physics and some chemistry of the ISM, okay? Things that I consider that are motivating, that are exciting, and that you probably need to develop kind of intuition, you know, to work in this field. So what you see is the ISM here. This is the Carina Nebula. So what we see at larger scales probably is dominated by the astrophysics, you know, by star formation and stellar feedback, meaning by the winds of this star. But what I like the most and what fascinated me more about the ISM is that the temperature, the densities here, the abundances of the atoms and the molecules that you see here are driven by the microphysical processes, okay? So ISM is a nice connection between the larger scales and really what happens at the level of molecules and atoms. So I'm coming from a new department. It's called the Department of Molecular Astrophysics in Madrid, downtown. So this is the people in our department. You may know some faces who have people working in the ISM, people working in protoplanetary disks, people working in galaxies, in molecular spectroscopy. And the good thing, I think, of our department is that we have real chemists, you know, theoretical chemists that help us to compute the reaction rates of the chemical reaction that we need or the collisional rate coefficients of the collisions we need, okay? So we don't have to ask anybody outside. You can compute these fundamental parameters of molecules inside our team. So if you one day would like to do a postdoc with us, it's a very nice place. In fact, 15 minutes walking from our institute, you can see the real stars, okay? So it's really easy to go there. And although some of these postdocs are not working as we expected, but well, let's see next year. All right, so this is the outline of my lecture. Some of the physics of the ISM, so which are the main components. You've been hearing this all the week, but it's not bad to hear the views of different researchers when you are working a topic, okay? It's like when you are studying something on ISM, it's good to read different papers from different people because different opinions will build your own opinion, okay? So heating and cooling, this is the first microscopic processes that determines much of what we see in the ISM, and this leads to the formation of kind of phases in the ISM, okay? Then I will go to the molecular or atomic excitation and radiative transfer. This is not the most exciting theory, okay? I will show simple equations, but they are really connected with deep roots into the quantum description of matter and the quantum description of electromagnetic fields. So we are astronomers, okay? So we collect photons. So this is the minimum you should know, okay? Very good. And then a little bit about interstellar chemistry. So Serena already talked about this. First thing is why we see molecules in the ISM at all. And for this, I will give you the basic theory or the basic description of gas phase chemical reaction. And I will try both for the radiative transfer and for the chemistry to show you some of the public models that you can use in your own laptop. Okay, there are very good books, sorry. Some are old, some are newer, okay? These are written by very good scientists, so Lyman Spitzer, Dave Williams, Alexander Tillens, Bruce. The American, the British, and the Dutch view of the ISM. So today you will get the Spanish view of the ISM. All right, so we live in a planet around a solar type star, okay? So our vision system has been developed to collect visible photons, okay? The photosphere of the sun has 6,000 Kelvin, so our vision system. So probably if we were orbiting a cooler star, our vision will have been developed to detect longer wavelength photons, but this is what we get, okay? We are sensitive. In particular, in the visible, we are sensitive to these tiny points, which are stars, probably because their photospheres have temperatures of about 10,000 Kelvin, okay? Extended emission, okay? These are nebulas, nebulosity, so extended ionized gas, like here in the middle is the Orion H2 region. So this is ionized gas that is also at about 10,000 Kelvin, okay? So people in the street will say, well, this is the sky, okay? Stars, dots. But we all know that the space between stars is not empty, it's full of gases, okay? In particular, I am interested in molecular clouds, okay? Meaning that it's gas with molecules and also dust grains. They are beautiful clouds, of course. They are fundamental for the evolution of galaxies, and the molecular gas is the fuel for star formation. Okay, these clouds are much cooler. Okay, so in particular in the fine infrared and sub-millimeter. Okay, the interesting thing is that these two very different components, the stars and the ISM, are coupled by photons emitted by the stars are absorbed by the dust grains in these clouds, and this energy is reabsorbed at longer wavelengths. Okay, this is an photometric way of saying the same. So this is roughly the spectral energy distribution, if you want, of the universe. Okay, and we have two peaks. Okay, one peak here at around 1 micron that is redshifted. I cannot do anything with the micro. It's telling you what is the energy released in the visible and ultraviolet. Okay, so this is produced by the stars. Okay, and there is another peak at around 100 microns and going into the sub-millimeter, which is so again, two components. In like more than 2 centuries observing the visible range, you know, the stars, but observing in the fine infrared is much more, I don't know. I mean, in fact, I took it for a paper, so I don't know how it's, so like, imagine it's photometry of, I don't know if it's a distant galaxy or.
The CIB at least.
Yeah, so this must be large, very large scales. What I wanted to say that we've been, do I microphone or?
No, I mean, yeah, because it seems that it works. See if it works better. Because I don't know why it.
Yes, okay. So we've been many years observing the visible domain from Galileo with telescopes. You know, observing in the long wave domain is much more complicated. We need technology, we need sophisticated detectors, receivers, okay? But the long wavelength part of the spectrum is extremely important for the ISM. All right, so I'm going to talk about the physics of the interstellar medium, not the science of interstellar, okay? So galaxies are not empty, you know? So the interstellar medium is everything that we have between the stars, so it can be matter, and I mean baryonic matter, okay? Not dark matter, which I don't really know how this dark matter interacts with the baryons. We have radiation, and we have, as you have seen, magnetic fields. So I am particularly interested in the gas phase components, so the atoms, the molecules, and the electrons, but we also have these small solid grains, which are small. They only make like 1% of the mass compared to the gas, but they are fundamental, okay? First, because they attenuate the ultraviolet radiation, so they protect the interior of molecular clouds from the ionizing radiation and from the ultraviolet radiation. And second, as you have seen, because the surfaces of grains are very good to create molecules, okay? To create chemical complexity in cold environments. Then we have the cosmic rays, okay? I don't know why they call it rays, because they are not rays, they are particles, okay? Very energetic protons, nuclei, and electrons traveling at high speed, at very high energies. In the ISM, we are mostly interested in these 100 mega electron volts cosmic rays, okay? Because the cross-section to ionize a molecule or an atom is inversely proportional to the energy of the cosmic ray. So it's the low energy cosmic rays, the one that will ionize hydrogen atoms and hydrogen molecules. And then we have radiations across the entire electromagnetic field. So the radio emission, mostly produced by electrons in these plasmas. We have the cosmic background radiation, which in our galaxy is 2.7 Kelvin now, but in your favorite galaxies at high redshift is probably higher. You have to compute that number. Fine infrared 2 millimeter, this is very important for the thermal emission of dust, so the dust grains that are heated by this ultraviolet radiation coming from the stars. The stars themselves, they emit basically in the visible and in the ultraviolet domain. Then we have the X-rays, which basically are produced by high temperature shock gas. Okay, so for example, supernova explosions will create shocks that will create plasma at a 1,000,000 Kelvin degree that will produce X-rays. And then we have the highest energy radiation, the gamma rays, that is funny enough that as you will see, it traces also the cold interstellar medium, okay? So here you have a view of the galaxy in very different frequencies. So low frequency in the radio domain, electrons. So this is the ionized gas in the galaxy. In the infrared, you see either the stars or the protostars, and then you have these dark patches, which is produced by all the dust extinction in the ISM. And cosmic rays here, this is the gamma ray emission, that it looks also like the electrons. This is because this gamma ray emission is tracing again interstellar clouds, okay? These very high energetic photons collide with the hydrogen atoms and hydrogen molecules, and they have so much energy that they create these unstable particles, pions, they call, that when they decay, they produce this gamma emission, okay? So this gamma emission is really telling you what is the interaction of cosmic rays with interstellar clouds. All right, so this, of course, you know, as galaxies evolve, the ISM is converted into new stars. This is the fuel for new star formation. And as the stars die, these stars, they return material to the ISM in form of chemical enrichment. So in our galaxy, because it's pretty evolved system, so 90% of the baryons are now in the stars. So the stars are more massive than the ISM, okay? So only 10% of the ISM of our, only 10% of the mass of our galaxy is in interstellar clouds, okay? So the stellar evolution and the ISM evolution are tightly connected, okay? For us, of course, everything starts in the ISM, in the diffuse ISM. For a reason that we still don't know, we are able to form dense molecular clouds that will form protostars. And as you know, there is 2 tracks for stellar evolution. There is one track that is very fast for the massive stars, let's say more than 10 solar masses, okay? These stars are not very numerous in the galaxy, but they make a very strong effect in their environment, okay? They live very short. I mean, they live very quick and they die young, you know, they are like rock stars, okay? So, but when they are in the main sequence, they produce so much ultraviolet radiation, and also they have stellar winds that inject a lot of radiative and mechanical energy into the environment, okay? And of course, they explode as supernova that also triggers the injection of mechanical energy and is a very powerful input of turbulence. But most of the stars in a galaxy are low mass stars, so stars like our sun. These stars, they go very, very slowly, and they develop protoplanetary systems, okay, in 1,000 million years. And they die also slowly in the form of red giants, which are very important, as you have seen, because we think that most of the dust are produced at this stage, as in Emmanuel talk, okay? So the stars and the ISM are coupled by the heating. This is one of the ways that the stars and ISM can couple, you know? The ultraviolet radiation from stars, the cosmic rays basically emitted by supernova remnants, and the shocks injected into the environment by stellar winds and supernova explosion, they heat the ISM, okay? They heat the ISM in a way that most of the gas has temperatures and thermal pressure that you can roughly think that they are organized in phases, okay? So the first phase is what we call clouds, okay? We have the cold neutral medium, where neutral means that hydrogen is in atomic form or in molecular form, okay? But it's not ionized, okay? So you can have this cold neutral medium, which is basically diffuse H1 and H2 molecular clouds, okay? This is one of the phases. The other one is also neutral, so hydrogen is also neutral, but we call it the warm neutral medium, okay? Then we have, I will explain in a minute, the warm ionized medium, where now hydrogen is ionized, okay? And then we have the hot ionized medium, hot meaning like millions of Kelvin. So this hot ionized medium is produced by the shocks produced by supernova explosion. But this is what we call the intercloud, okay? So we have the clouds and the intercloud medium. So these phases depend on how the gas is heated and cooled. And as I told you, this depends only on microphysical processes. If you want to understand let's say, the thermodynamics of this region, you have to understand how the gas is heated and cooled in different environments. And the important thing is that how the gas is cooled depends on the chemical composition of the gas, okay? And on how a molecule or an atom can radiate a photon, okay? So that's why chemistry and spectroscopy is also important. So much of what we do in the ISM is try to understand, of course, the microphysical processes, so how stars form, what is the impact of stellar feedback, winds, ultraviolet radiation. But also we need to understand all the detailed microphysical processes that form a molecule, that destroy a molecule, and they excite a molecule or an atom, okay? So this is taken from Bruce Drain's book. So this is the flow of energy in a normal galaxy like ours. So basically you see the stars will be producing a lot of energy in the form of stellar radiation that will be injected into the ISM. Stars, especially the massive stars, they have winds, so they also inject mechanical energy in the form of turbulence. So in the ISM, we have different types of energy: kinetic energy, thermal energy, chemical energy. We have turbulence, we have magnetic fields. So the density of all these energies is quite similar, about an electron volt per cubic centimeter. Okay, so some people may think that this is a coincidence, or some people may think that all these energies are related, okay, because they look all the same. So the ISM is not a stable system. It's not happy with all this energy. It will try to get rid of this energy by radiating to the environment, okay, to the cold sky in Bruce's book, okay. So this, by dissipating these energies, one way of dissipating is emitting light from gases and continuum, for example, from the dust. So it's as the astronomer that by observing this line and continuum photos that we can try to go up and understand all these different energy inputs. The important thing is that the densities are so low in the ISM compared to the density in this room, okay? And also we have ultraviolet radiation, we have turbulence, we have cosmic rays, that the ISM is not in equilibrium, okay? In equilibrium for us in thermodynamics will mean that with a single temperature, you can define the state of a gas or an environment, okay? In the ISM, because of these low densities and all this energy input, the gas temperature normally is not equal to the excitation temperature that tells you how atoms and molecules are populated, okay? And it's different than the ionization temperature that tells you how different atoms are ionized, okay? So it's not in equilibrium. So it's our job to study all the microprocesses, to balance all the microprocesses and to determine this temperature. So to determine the gas temperature, we need to know what heats the gas and what cools the gas. To understand the excitation temperature of molecules, we need to understand what excites a molecule and what de-excites a molecule. And to understand the ionization balance, we need to know what ionizes the gas and what recombines the ions. Okay, so very important, the ISM is not in equilibrium. Okay, so the phases in our galaxy. So I will focus on our galaxy now. So most of a significant part of the mass is in ionized gas, H+ here. So yesterday we had a nice talk about all the ionized gas in galaxies. Today we'll focus more in the neutral medium. So 60% of the mass in the galaxy is in atomic hydrogen, and almost 20% is in molecular hydrogen, okay? So the volume filling factor of these phases scales with the density, okay? So the lower density phases will occupy galaxies, okay? And the densest components, like the molecular clouds, will be only a minor fraction in volume. So let's see a summary of these phases. So we have this hot intercloud ionized gas, okay? You see very extremely low densities, but very high temperatures, about 1 million, okay? That's why this gas was called coronal gas, okay? Because in the corona of the sun, they also discovered very ionized material. So this ionized gas occupies like 50% of the volume of the galaxy. Then we have the warm neutral medium that you see we now go to low densities and warm temperatures of about 8,000 Kelvin, large volume, 30% of the galaxy, and these components start to be really massive, okay? So like 3×10⁹ solar masses. A very similar component is the warm ionized medium, where now here hydrogen is ionized, okay? But the temperatures and densities are roughly the same. And then we go to a place where molecules start to form, the cold neutral medium, so higher densities, something like 50, much lower temperatures, something like 100 or 80. And you see that there is a significant amount of mass in this cold neutral medium. In some parts of the cold neutral medium, we will have molecular clouds, so dense molecular clouds. These are the entities really that lead to star formation. They have a lot of mass, well, a significant fraction of the mass, okay, but they occupied a fairly low volume in the galaxy. And it's only around the most massive stars in these molecular clouds that we can have what we call H2 regions. So it's ionized gas at a high density, okay, H2 regions. So if you focus only in the warm neutral gas and in the cold neutral medium, you can define the thermal pressure, that is only the product of the temperature and the density. And you have, if you multiply these two numbers in orange here, you see that these two components, roughly, they have the same pressure. Okay, so we say that the warm neutral medium and the cold neutral medium are in pressure equilibrium. Okay, very good. But you have to know that all the properties, the masses, and the filling factor, of course, these are not exact numbers even for our galaxy. So there is a lot of research. In fact, I guess that you are studying also probably these phases in your favorite galaxies. So today I'm focusing in the neutral ISM. So hydrogen is atomic or molecular, but not ionized. Okay. So I'm going to tell you more about dense molecular clouds, diffuse clouds, and the intercloud warm neutral medium. So to understand how the gas is heated, you have to understand the radiation fields emitted in the ISM. So most of the ultraviolet radiation field come from massive stars. Okay, massive stars means OOB stars. Okay, they emit two different kind of ultraviolet radiation. So we call the extreme UV radiation. So photons with more than 13.6 electron volts. And this is really the boundary to ionize hydrogen. So this extreme UV radiation ionizes hydrogen and produces H2 regions around the stars and the extended warm ionized medium. For molecular clouds, we are more interested in what we call the far ultraviolet radiation, which are photons with less than 13.6 electrons. Okay, so these far UV photons can penetrate inside molecular clouds, but they will not ionize hydrogen. Okay, to check whether an atom or an element will be ionized, you have to check the ionization potential. Okay, so you see, for example, for hydrogen and nitrogen, these elements will be neutral inside molecular clouds, okay? But inside molecular clouds, so we have photons with less than 13.6 electron volts, these far UV photons will be able to ionize carbon and sulfur, okay? So although we say neutral clouds, you see that a small fraction of the gas is ionized, so carbon atoms can be ionized. So we define the far ultraviolet radiation field with this G0 value, the Having field, okay? So roughly in the mean interstellar radiation field in an average position of the solar neighborhood is something like G0 equal 1. But if you are close to a massive star, we say that G0 can be like 10 to the 4, 10 to the 5. So how the gas is heated? So the gas is heated by what we call the photoelectric heating mechanism. So these far ultraviolet photons penetrate inside the neutral clouds. They impact a pH or a small grain, ejecting a photoelectron, okay? So this photoelectron will carry an energy of a few electron volts, so will be energetic, and this electron will collide with the molecules and with the atoms heating the gas, okay? So the most important heating mechanism of the neutral gas at large in a galaxy, okay, not in your favorite spot, is the photoelectric heating mechanism, okay? So Einstein, this clever man, you know, he was very busy trying to prove the general relativity. He got the Nobel Prize because of the photoelectric heating, because of the photoelectric effect on metals, okay? But he did not know about the ISM heating, okay? And we can say that he also got the Nobel Prize because he set the basis to understand how the neutral gas is heated. Okay. So how the gas is cooled? Okay, we go now to a microprocess, another microphysical processes. Cooling means that you have, for example, a gas with a two-level system, okay? So most of the molecules or atoms will be in the lower energy state. These molecules will collide inelastically with a molecule, with an atom, and producing a photon, okay? And if this photon escapes the cloud, this transfer of energy from a collision to a photon will be cooling the gas, okay? This is how molecular clouds are cooled. All right. So the collisions with atoms, ions, and molecules with these photoelectrons heat the gas, okay? Excite the gas. And then the emission of a photon in these different levels produce a photon, okay? So in the warm neutral medium, okay, most of the atoms, for example, hydrogen, are excited to electronic levels, okay? And the way that the warm gas has to cool is to emit a Lyman alpha photon, okay? So in these warm regions, most of the cooling is produced by hydrogen, okay? If we go inside the cold neutral medium, atoms, some specific atoms with an ampere electron, they have fine structure levels of much lower energy than the electronic levels, okay? So in particular, carbon plus, ionized carbon has an hyperfine doublet with an energy separation of 92 Kelvin. And this emission in the famous C+ line is responsible of the cooling of the cold neutral medium. And in fact, it's only because carbon plus has this structure, these fine structure levels, that the cold neutral medium has this temperature of about 80 Kelvin, okay? Then inside molecular clouds, we need to cool the gas in order to form stars, okay? And molecules, they have another degree of freedom, and molecules can vibrate and they can rotate, okay? So the energy separation of the molecular rotational levels is at much lower energies, okay? So for example, the first rotational levels of CO, the difference between levels is only a few kelvins, okay? So the emission of CO photons at these low energies can cool molecular clouds to 10 kelvins, okay? So clouds or different environments have the temperatures they have because these different atoms, ions, and molecules, their emission can cool the environment. All right, so how do we determine the gas temperature of a system? This is what we call the thermal equilibrium. So we have to say heating equal cooling, okay? You see that the cooling here depends on the density. So for a diffuse gas, it will have more problems in cooling, okay? But a dense molecular cloud will be cooler also because the cooling depends on the density, okay? And remember that we define the gas thermal pressure as the product of the density and the temperature. So if we plot the regions allowed by this thermal equilibrium, so heating equal cooling, you get something like this. So in the x-axis, you have the density of the environment or the density of the cloud. So this you see 10 to the minus 2. This means really a very low density environment, okay? And here you have densities of 10 to the 3. So here in the upper panel, we have in the y-axis the thermal pressure, okay? So the gas will be able to be in this curve, okay? This is density against thermal pressure. This is a little bit small and busy here, okay? But you have here is the different heating and cooling mechanisms depending on the density of your cloud. So here in pink is the photoelectric heating that I just mentioned. So this is stellar UV photons producing photoelectrons and heating, okay? So it dominates in almost all the density range. At very low densities, cooling is dominated by Lyman alpha, so hydrogen atoms cooling, okay? But as you increase the density of the cloud, most of the cooling is carried out by the carbon plus line, okay, 158 microns. But you see here that we can have a range of pressures, of constant pressures, where the gas can be in two different environments, two different densities, okay? And this is what I was mentioning at the beginning. This is the warm neutral medium at T equal 8,000 Kelvin, so low density, warm temperatures, or you can be in the cold neutral medium, so higher densities and lower temperatures. I think this plot is better again. So this is the thermal equilibrium, okay? This is nice because here in this plot, they plot the isothermal lines, so regions where the gas has a constant temperature, okay? So in this domain, the warm neutral medium, the gas is mostly atomic and warm, so close to 10,000. In this other domain, the gas is also stable, but it's much cooler, okay? In pressure equilibrium. So if we are in a constant pressure environment, we can have these two solutions, okay? And in the middle, we have kind of unstable gas that will try to go to either of the two environments. So the warm and neutral gas is mostly atomic, so mostly H1. The cold neutral medium is mostly molecular, okay? But then we go to the dense molecular clouds. You may be more interested in these ones because these are the ones that form stars, okay? These are the ones you may detect in HCN and HCO plus with your ALMA observations. So this is not a really a new phase of the ISM, okay? Because these clouds are self-gravitating, okay? It means that the pressure, the internal pressure is higher than the ambient pressure, okay? So they are not in pressure equilibrium with their environment. So in these clouds, especially when there is sufficient material, so sufficient shielding, the heating is not anymore dominated by the stellar photons because UV photons cannot penetrate really inside molecular clouds, okay? So what dominates the heating of these dark clouds is cosmic rays, okay? Cosmic rays impact and also produce energetic electrons that can heat the gas, but only up to 10 Kelvin, okay? So that like the minimum temperature you can have in a molecular cloud heated by cosmic rays with a standard ionization rate is something like 10 kelvins, okay? And now the cooling is not by H1, the cooling is not by C+, the cooling in cold environments is by the molecules, so for example, CO. So this is the classical multi-phase model of the ISM of a galaxy, where we have the cloud phase, so the cold neutral medium, and all the intercloud component, the warm neutral medium, the warm ionized medium, and the hot ionized medium. Okay. So this model you see is classic because it goes from the 70s. You know, it was driven by McKee and Ostriker, related to how supernova explode in a galaxy. And yeah, you have to figure out that dense molecular clouds is only like a 20% of the mass of these phases, and they go to much cooler temperatures. But this is a classical model, okay? In fact, today we know from observation by the simulation the product you saw last week that the ISM is much more dynamic and turbulent, okay? So you can have changes of phase and you can have mixing between the different phases, okay? In fact, from observations, we detect atomic hydrogen in the thermal unstable regime, so in the green curve that I showed you before, okay? So people now try to understand the properties of the ISM through these magnetohydrodynamic and turbulent simulations that probably you saw last week. Turbulence is a very complicated problem, okay, because it's generated at very large scales. So you can imagine the explosions of supernova injecting mechanical energy at very large scales, but turbulence dissipates at the very small, almost molecular scales, okay? So all this turbulence at the end can be converted into heating of the molecular gas at the small scales. So it's very difficult to model, okay? In this field, shocks can induce phase transitions between one phase to another, and inside a molecular cloud, it can trigger shocks, okay? We know that the turbulence is supersonic, okay? Meaning that the line widths of the molecular lines that we detect with our telescope normally are broader than the line widths that the thermal energy will imply, okay? So there is normally supersonic turbulence, and this supersonic turbulence triggers shocks, okay? So the ISM is not so quiescent. So this is one kind of high-resolution simulation that is already from 2022, okay? So maybe this is the way you should see the ISM, okay? You have to imagine the ISM like this. So in these simulations, they were following the dissipation of turbulence from the supersonic turbulence, and they were looking the spatial scales at which the turbulence becomes sonic, okay, not supersonic. And this is important because in the regions where the turbulence becomes less important, so sonic, these are the regions where gravity can start to win and can trigger the collapse, okay? So in our ISM, thanks to many studies of stuff forming filaments, you know, we see that the width of these filaments, they have a width of about 0.1 parsec, you know, and this is the scale where the turbulence becomes subsonic, okay? So regions where gravity can still win if the magnetic field is not super high. Okay, so now let's try to define molecular clouds. We use the extinction by the dust. I told you that the dust shields molecules from UV radiation. So when you have standard grains, you have this relation. So you can relate the column density of material with the extinction in the visible, okay? Of course, if you have low metallicity or you have bigger grains, this number will be difficult, okay? Sorry, it will be different. But this extinction in the visual gives you an order of magnitude on how to define molecular clouds. So if you have a cloud with less than 1 magnitude of extinction, we call it a diffuse cloud. So in a diffuse cloud, you still have a lot of visible and far ultraviolet photons permeating this environment, okay? So the gas will be neutral, meaning the hydrogen will be neutral, but most of the gas will be in H1 and not in H2. So between 1 and 4 magnitudes, this is the translucent regime or the PDR domain where the far ultraviolet flux is still significant, okay? But now the chemistry can produce H2. So most of the hydrogen will be in H2. And then clouds with extinctions between 4 and 8, then we enter into the regime where the ultraviolet radiation field is mostly shielded, okay? So UV photons will not affect much the chemistry. So this is what a typical PDR model predicts for this kind of environments, and this is a way also of understanding the different components of the ISM. So remember that massive stars produce extreme ultraviolet photons that produce H2 regions, but here in the neutral ISM, we only cared about the regions where only the photons with energies below 13.6 electron volts penetrate, okay? So hydrogen will be neutral, but because of the ionization potential of carbon, still most of the carbon will be in C+, okay? So this is the diffuse medium where most of the hydrogen is H, is hydrogen, although the abundance of H2 is starting to rise, okay? So here, there's not much chemistry, but this is mostly atomic. In the other side, we have a region where now most of the hydrogen is in molecular hydrogen, and we have also converted a significant fraction of the carbon into carbon monoxide, okay? So in the last year, we realized also the importance of this other intermediate layer where the gas is molecular in the sense that most of the hydrogen is H2, okay? But the abundances of CO are still very low, okay? So very low means that we cannot detect this CO with our radio telescope. It doesn't mean that there is no CO, because for me, in fact, the most exciting result is that you start to form molecules here, okay, at the very edge, although molecules like H2 and CO, they have very low abundances, okay? But as soon as you have some shielding, you have molecules. But this domain is peculiar because CO is so underabundant that you will not detect it with a radio telescope. But still, we don't know how much fraction in galaxies we have of this molecular gas that we don't see in CO. And this may be important, an important reservoir of the baryonic matter in galaxies, okay? So molecular gas that we cannot detect in CO. So big questions in this field. So how are these molecular clouds assembled from the diffuse gas into the denser gas, and how this dense gas ultimately form a star? So this is still a valid scientific question. We don't understand all the details. Although now we have telescopes, so with such a high angular resolution that we also have like other kind of questions, like how do planets form? Okay, in protoplanetary disks, for example, we start to see how planets start to assemble matter. Okay, how do the different energy sources, so the ultraviolet, the thermal, the cosmic rays, the turbulent, the magnetic fields, and the gravity contribute to the dynamical properties of the evolution of the ISM? Important question also. And what's the role of the feedback process? I mean, feedback means the injection of energy in the form of radiation or momentum. Is this feedback positive? I mean, does it trigger a star formation, or is this feedback negative? Does it quench a star formation? And for those that we use molecules as a tracer of astrophysics, also we like to know what are the limits of chemical complexity in the ISM. So how are the molecules already formed, and how what the different molecules trace. So to answer this question, we need, of course, observations. Okay, so this observation of the Milky Way, because we are inside the Milky Way, it's difficult to observe the Milky Way, but you have these nice H-alpha surveys, okay, telling you what is the distribution of the warm ionized medium. So this is very diffuse ionized medium, much fainter than typical H2 regions, but you see it occupies a large region of the galaxy. Then we have the cold neutral medium. You can measure this with the C+ line. This is the most important and the brightest line of the ISM, okay? But unfortunately, this map of the galaxy was done with COBE, many years ago with a resolution of 1 degree, so very small telescope. And it's impressive that this line in the far infrared, the brightest line, the most important line, we don't have any telescope to observe this domain, okay? We don't have Herschel anymore. We don't have Sophia. So we don't have anything to observe in this very important domain that is the peak of the spectral energy distribution and where the cooling lines of the ISM appear. Okay? So maybe with PRIMA in the future. And then we have the molecular gas. So this is, I don't know if you see it, but this is again our galaxy. So in blue, you have the CO emission, okay? And in colors, you have the dust emission. And you see more dust emission than CO. Okay, in fact, there is an excess of the dust emission over CO and over the H1. And this is possibly what I was telling you. This is molecular gas that we cannot observe in CO, but it's there. Okay, so it's the CO dark molecular gas. So some people think that maybe between 20 or 80% of the molecular gas in a galaxy. This depends on how CO is destroyed. So it depends on the photodissociation of CO. And this depends ultimately of the metallicity of the galaxy, okay? For lower metallicity, more UV penetration, more CO destruction, so more CO dark gas. Of course, then we have the magnetic fields. So probably you saw this one, this very Van Gogh picture, where you see in colors the dust emission, okay? So the dust produced by clouds in the Milky Way, and the texture here is the orientation of the magnetic field, because now you know that grains are not spherical, okay? They are elongated. So their minor axis align with the magnetic field, and this produce a linearly polarized emission. Planck was not a very big telescope, okay? So we have these magnetic field maps at medium angular resolution, where we see that in the low density filaments, the magnetic field is roughly parallel, but in the dense filaments, where maybe you have a star formation, magnetic field is perpendicular. So maybe it's telling you of how the matter is channeled in these environments. All right, so you have to know that most of the wavelengths carry information about the ISM. So in my times, when I was a PhD student, they were telling me, are you a radio astronomer? Are you an infrared astronomer? So this question these days doesn't make sense, okay? So in order to understand a problem and try to solve it, you have to try to mix all the different wavelengths, You have to integrate in the same picture emission from hydrogen, from the dust, and so on, okay? So you have to try to use all possible wavelengths. So to understand how photons come to telescopes and what this means, we need a little bit of rapid transfer. I don't know if we can stop for if anybody has an easy question. So I can follow.
Yeah, thank you, Javier. Maybe a question about the dark CO and that you associated it to C+. So what is the fraction of dark CO that is seen through C+?
Yeah, I forgot the number, but it's something that it's done, for example, by Paul Goldsmith and the group. But I think it's like we miss like 30% of this CO gas in our galaxy. But you need C+ and you need also observation of H1 to really pin down.
But if you would have, let's say, in a dream world, an extremely high resolution map of C+, would it solve the CO dark?
You have to combine this always with observation of H1 also and the dust. But this is one. Some of us in Europe, we are advocating for a telescope with a very high resolution spectrometer, so heterodyne, that it's able to map C+ and oxygen-1 in the Milky Way, for example, to do a survey in 3D, so we can really determine how much CO dark gas we have as a whole in the Milky Way and where it's located. Is it in the halos of molecular clouds?
Okay. Thank you.
C1 is complicated because in the models, it's always looking like in the middle of the sandwich, But in real observation, C1, you see it also, it seems like to exist also deeper inside molecular clouds. But yeah, of course, yes, because this will be a region where the CO is lower. So
yeah, maybe I missed something fundamental, but why C+ is so important?
Why? Because it's the dominant coolant of the cold neutral medium, okay? Because C+ is very abundant, it's like after oxygen is like the next most abundant element. And because it has an ampere electron, this means that it not only has electronic levels, but it also has lower energy fine structure levels. But it's very simple, it's a doublet, And this doublet happens to have an energy of 92 Kelvin, And the combination of this doublet is easy to excite, so an emission of this doublet can cool the medium. And the fact that the C+ is so abundant, if you make the numbers, makes it the most important gas coolant, in this environment, cold neutral medium. So the medium that you observe at 100 Kelvin is 100 Kelvin because C+ is cooling the gas. And we know this also because the associated line, this far infrared line, 158 microns line, is the brightest line in these environments, So it's C+. Imagine a galaxy without C+ or without carbon, the cooling will be different, the temperatures and the pressures will be different.
Okay, I see. Thank you.
Yeah.
Early on, you showed a diagram from Bruce Strain's ISM book that showed like it said like a diagram for like normal galaxies. How do we define normal? Like, where does that break down? Like interacting galaxies like high redshift.
Very good. I had to put this normal word because I'm not extragalactic. So for me, normal galaxies are galaxies without, an AGN and without extreme star formation rate, So something similar to our Milky Way, yeah. Very good question, yes.
Other comments, questions?
Okay, then we go back to some of the equations. Not many, because I told you these are simple, but it's something that you have to integrate in your way of thinking if you want to be astronomer. So it's about excitation and radiative transfer. So any molecular cloud in your favorite galaxy will emit photons. We will try to detect with radio telescopes, and we detect this emission as lines, transitions, molecules, they produce lines at given frequencies. The purpose of understanding radiative transfer and excitation, and the purpose of using radiative transfer models is to go back, and use this emission and these models to determine the gas density, the gas temperatures, the abundance, and the velocities of these molecular clouds, okay? So the equation of radiative transfer is very easy, as you see. I mean, the most important magnitude is the intensity of radiation that you have here in the CGS system. And this is the equation of radiative transfer, for a slab of gas containing molecules, okay? We may have some background emission here in the back, and we are interested in detecting this intensity. So in this simple equation that is tell you how the intensity is propagating in this scale, we have the absorption coefficient, and we have the local emissivity term here, okay? So now we define the opacity of, for example, of a line, which is a very useful term because it's dimensionless, okay? So it's the absorption coefficient multiplied by the length scale. And we define the source function, which is only the ratio of the emissivity and the absorption, okay? So with these simple definitions, the equation of radiative transfer is even simple because we can define how the intensity propagates, but this time as a function of opacity, which has no dimensions, okay? So you go to the textbooks, and you find this is the formal solution of the equation of radiative transfer, but for me it doesn't help much. It's only like the equation of radiative transfer in integral form, okay? But okay, it's the formal solution. So if your medium is homogeneous, meaning that the temperature is constant, the abundance doesn't change, this solution is so simple as this one, okay? So the intensity that you will detect here is only the background attenuated by exponential tau, and then these other terms tell you all the absorptions and emission inside this box full of gas. Okay, pretty simple. So this equation tells you the effects of matter, so through the source function and tau, on the radiation, how matter affects radiation, but it doesn't tell you how radiation affects matter. You will see this later. So we need limits. So as you know, if we have very thin amount of gas, okay, a thin layer of gas, you can expand this solution and put that tau goes into 0. And basically then the intensity of radiation will be that you will detect will be the background multiplied by something that is proportional to the opacity. So proportional to the amount of gas that you have in the line of sight. However, if the opacity is very high, you lose all the information on the background and you only detect the source function. Very easy to understand. Optically thin, you see the background and what is in between. And when you have optically thick and opaque medium, you only see what we say the surface of tau equal 1, okay? But you don't know anything about the background. Very nice. So now let's think that the gas is only a two-level system. So from the point of radiation, okay, we have two energy levels, okay? In nature, we'll tell you normally that the lower energy level is more populated than the excited level. But if you have excited molecules here, they can emit a photon, and this is given by the Einstein coefficient of spontaneous emission. But also this gas can absorb a photon, so you can have a stimulated absorption. And sometimes you can absorb a photon producing a stimulated emission. So these A, B, are, as you know, the Einstein coefficients with these relations here. Of course, the lifetime of this high energy, of this excited state will be the inverse of the Einstein coefficient, okay? So this will be the inverse within seconds. So 1 divided by 8 gives you the lifetime of any molecule or any atom in the excited state, okay? So these are the relations of the Einstein coefficients. So the number of stimulated absorptions or emissions are the B Einstein coefficient multiplied by this J, which is the average intensity of radiation over angle and over line profile. Okay, so A given transition will emit a photon at a given frequency, but in the ISM, gases are moving, because of we have a temperature. So this means that gases have random motions. Okay, so these random motions can be converted into different slight variations of the frequency. Okay. Also, if the gas has some microturbulence, okay, the gas will be moving, so not all photons will come at the frequency of the transition. Okay. So if the motions are thermal, meaning that the gas follows a Maxwellian distribution and the turbulence is microturbulence, this line intrinsic light profile will be given by a Gaussian of a given line width. Okay, this is what we have here. So when we talk about mean intensity, is the mean intensity of radiation over the line profile and over all solid angles. Very good. So how do we go from these absorption and emission coefficients, which is something macroscopic, to really microscopic properties of matter? This is through the definition of the emissivity. The emissivity, we need to know how many molecules we have in the upper state here and how fast they radiate. That's why we have N up multiplied by the Einstein coefficient. And to understand the absorption coefficient, we need to know how many molecules we have here in the low energy level, multiplied by the stimulated absorption coefficient, and corrected by the fact that we can have some molecules here excited and they can also emit. Okay? So this is the microscopic definition of the emissivity and the absorption that we use in the definition of these parameters. Now, in LTE, most of the levels will follow a Boltzmann distribution. I guess you know this, a Boltzmann distribution at the gas temperature, at the gas kinetic temperature. Okay. But it's very useful to define, and this is a definition, okay? This is nothing fundamental, to define the excitation temperatures like this, okay? Level populations, this exponential, and Tx, okay? We don't know in the ISM how the molecules are populated. We don't know if they are in LTE or whatever, okay? But we define the excitation temperature of two levels like this, okay? It's a definition. So this means what I told you before, if normally in nature, the lower energy levels are more populated than the excited ones. So this means that the excitation temperature, according to this definition, will be greater than 0, which means that the absorption coefficient will be greater than 0, which would mean that the opacity is greater than 0. Okay, so when we have a lot of molecules in the ground state, this will produce absorption. Okay, this is what we call thermal emission, so normal population, meaning that always the upper levels are less populated than the lower energy levels. But sometimes we can have this kind of properties that we have more population in the upper level than in the lower, okay? So if you make numbers here, this will give you a negative excitation temperatures, but we don't care much because this was our definition, okay? So it's negative, okay, why not? And this will give you a negative opacity. Okay, so in the equation of radiative transfer, all this component exponential minus tau will be now exponential plus tau. Okay, so instead of absorbing, this exponential plus tau will be like an amplification. Okay, so when populations are inverted, we can create a Maser emission. Okay, so instead of absorbing emission, we increase the emission in our system. Very good. So now we go back to the source function. That was this particular term in the equation of radiative transfer. So telling you the absorptions and the emissions in the slab. So you can use this definition of the emission coefficients and the absorption coefficients in the definition of the source function. And you can also introduce our definition of excitation temperature, and magic, you reach a Planck law distribution at excitation temperature. So the source function is nothing else than a black body at an excitation temperature Tx. Okay, this looks very simple. This looks very helpful, but we still don't know what is Tx. Okay, but this is the source function: a black body at the excitation temperature of two levels. So in reality, the equation of radiative transfer tells you how this intensity of radiation propagates in a medium. Okay, now if you are a radio astronomer, you are handling with radiation that has very low frequencies. Okay, lower than this. So this means that you can expand all these exponential terms in the Planck function and reach a definition of the brightness temperature. Okay, I don't know if you see it, but this is useful because now we have the brightness temperature is proportional to the intensity. So there is no exponentials in between. There is nothing. In fact, this is like a classical result of physics, because in this expression, you will not see the H Planck constant, okay? So that's why in radio astronomy, instead of working with intensity of radiation, we can convert into the equation of radiative transfer into temperatures. And this is also related to the way we calibrate our observations and the way we calibrate our receivers. So the equation of radiative transfer will be like this. We detect a brightness temperature with a radio telescope. Instead of an intensity of the background, we have the background temperature. And instead of the source function, we have the excitation temperature, okay? Now, in astronomy, we always do either on minus off observations, or we remove a baseline. So we always have a control on the background temperature, okay? So in fact, what we detect in telescopes after subtracting a baseline, you have here the continuum level at 0, is something that is really the brightness temperature minus the background, okay? This is what really we observe, okay? So the equation of radiative transfer is very simple. When you are interested only in the line emission, this will be the solution. And the limits, in the optically thin limit, of course, the brightness temperature will be proportional to the excitation temperatures and the opacity. So basically, an optically thin emission will trace the excitation and the amount of column density that you have in the line of sight. However, if you have optically thick emission, then the line intensity will the observed line intensity will only be proportional to the excitation temperature, okay? So you are not sensitive to the background, and you are not sensitive to the amount of material that you have. You are only sensitive to the excitation properties of the molecule. Okay, so how are really the population levels, therefore the excitation temperatures determined? This is really the key question. How are the different atoms and molecules excited? One very easy way from observation is the rotational population diagram, but I'm not going to explain this because I have a very group of smart people in our hands-on session, so they will do it on Thursday, okay? Thanks to Miriam and to the people in the group, so wait for Thursday. So a two-level system, so a molecule can be excited by radiation. We have seen this before, so this is the effects of radiation of matter, you know, the way a molecule absorbs photons or not. But molecules or atoms can also be excited by inelastic collisions with something else, okay? Normally with the most abundant molecule in the environment, so normally H2. So really to understand how a molecule is excited, you need to know the collisional rate coefficients, okay? Which is these gamma values. So the number of collisions will be gamma multiplied by density, but this density is the density of the molecules that are colliding with you, okay? So H2 normally. Or electrons if you are in an H2 region, for example. So you have radiative transitions and collisional excitations and collisional de-excitations. So the way we compute the level population is solving what we call the statistical equilibrium equations. Okay, so basically you have to put in the same equation what populates a level and what depopulates a level. Normally, this derivative is equal to 0 because in time, normally these excitation processes are much faster than the time you need to change the molecular abundances or the physical conditions. Okay, so all you have to solve is the equation of radiative transfer to give you these J numbers, this intensity, and you have to solve these statistical equilibrium equations. So what limits can we have? Okay, so if we neglect all the radiative transitions, so we only assume that the collisional rates are much faster than any radiative rates, so you remove all the radiative transitions, you are left with this equation, which means that if only collisions are important, the populations of the levels follow a Boltzmann distribution at the gas temperature. This is the definition of LTE, okay? So when collisions are very important, meaning in very dense gas, then all the excitation is very simple because it's only a Boltzmann distribution at the temperature of the gas. So to play this game, you need to know the collisional rate coefficients. Okay, that is like the cross section of the collision multiplied by the temperature, by the velocity or if you want the integral of the cross section over the Maxwell distribution. Okay, the astronomers we don't know how to compute these collisional cross sections. Okay, that's why you have to be friend of theoretical chemists that can help you and can provide these numbers. Okay, this is computed by quantum methods. So the other limiting case is where you don't have collisions, okay? So very low density medium, and the only important thing populating and depopulating is the absorption or the emission of photons. So the only background radiation is the background temperature, okay? And you make numbers here, and what you get, in this case, in the low density limit, levels are populated according to a Boltzmann distribution at the temperatures of the background, okay? So the populations are thermalized radiatively, not to the gas temperature, it doesn't care about the gas temperature, but to the background temperature, okay? These are the two limits. So there are many, well, many, no, that some radiative transfer models in the market, okay? They are only different in the way they compute the mean this J number, the mean radiation field, okay? Because this radiation is produced by all the molecules in the cloud, okay? So in theory, to compute this J number, this intensity of radiation, you need to compute the level populations in all the cloud, you know? And this is not so easy. So the first approximation is what we call local radiative transfer models, okay? Meaning that we don't care much about what happens in the environment, okay? And all the absorptions and emissions are produced locally. Okay? This is the famous RADEX molecular radiative transfer model. I don't know if you use it. It's an LVG model, meaning large velocity gradient, meaning that you have a sphere that is expanding at such velocity, okay? That when you emit a photon, the next shell will be at so much higher velocity that these two photons will never interact in velocity space, okay? So you can decouple the radiative transfer, and the only thing that matters really is the excitation at a given position. This is called the local excitation code. So I'm not going into much detail here. And these are approximated models, okay? But they give you an answer in 1 second. Okay, this is because they consider that all the excitations are produced locally, and in fact they don't solve the equation of radiative transfer for J. Okay, there are other models that like Monte Carlo that spend all the computational time trying to simulate the intensity of radiation in the cloud and following exactly how many absorptions and remissions you have in the cloud. These are much slower methods, okay, but they are very flexible because you can define a sphere or a square, whatever. You can include velocity fields. There are ways of accelerating these models, but I'm not going into these details. And in the last year, there has been a very clever and very smart way of approaching radiative transfer that I think it killed the radiative transfer forever and ever, which is called the couple escape probability. That is based on these LBG models, you know, but they include a correction factor for the coupling between the emission and different shells, okay? And these models, like the LBG, they don't really solve the equation of radiative transfer, okay? They convert all the problem of the statistical equilibrium equation into algebraic equations, okay? And by defining escape probabilities and how the different shells interact, okay, they give you the exact result, okay? So I think today the radiative transfer is mostly done, okay? So this program is public. It's called MolPop. It's true that it's only working so far in slab geometry, okay, plane parallel. It doesn't include velocity fields and sophisticated things like line overlaps, okay? But this is free, and it provides an exact solution for the population for the radiation field, you know, in seconds. All right, so don't try to use only radiative transfer models without thinking before, okay? There are ways that you can see how the excitation of your molecule will be. And one of the most simple ways of thinking in the excitation of molecules is by this definition of the critical density, which is the density at which spontaneous emission equals collisional de-excitation, okay? In principle, this is a definition with two parameters that only depends on the molecule and on the level that we are considering. Okay, there is no astrophysics here. These are fundamental constant of a molecule and has units of density. Okay, so you can play with this and insert this critical density into the equation of statistical equilibrium. And if you are in a medium where the gas density is much higher than the critical densities, then collisions will dominate the excitation. Okay. And then the excitation temperatures of the molecules will approach the gas kinetic temperature, okay? So this is the LTE, okay? So for this, you have to tabulate and you have to know which are the critical densities of your favorite molecules, you know, to see if you can use them to trace dense gas or to trace diffuse gas. So if the gas density is much lower than the critical densities, then collisions will not play a role, okay? Molecules will not see other molecules around it, and the excitation will be dominated by radiation excitation. So the excitation temperatures that you will get are lower than the kinetic temperatures. This is what we call the subthermal emission, but this is the interesting range because here, by playing with the models, we will be able to extract the density of our medium. Okay, so here the molecules will be, the molecular emission will be sensitive to the density of the medium. There is an important effect that is called line trapping. Okay, so normally in an optically thin line, your molecule will emit a photon that will escape the cloud. Okay, so you're happy. It's optically thin. In fact, this photon will be cooling the cloud. But if you start to have more and more column density of material, okay, the opacity of your line will increase. Okay, so these photons that in the optically thin case were escaping the cloud, now they will be able to be reabsorbed in the same transition. Okay, they will be trapped by the transition. Okay. So somehow the population of this upper level will be increasing, okay, as you increase the opacity. This is called line trapping because photons don't escape, they get trapped, and they increase the population of this upper level. Okay, so in fact, this depends only on the molecule, but in fact, in the ISM, what we care is about the effective critical density, okay, that depends on this line trapping effect. So normally the effective, so the real critical density is the critical density that you compute this way divided by the opacity, okay? So as you increase the opacity, there is more line trapping, so the excitation temperatures will increase, okay? So you have to consider this when you talk about critical densities. Don't forget to see how much gas you have, because maybe the effective critical density of your transition can be lower, and what you think is a dense tracer is not such a dense tracer. So in most cases, you have solved the statistical equilibrium equations with a model. So you have Radex. You can download this small pop, okay, and start to play with these models. So this is what happens with, you have different kind of molecules. I don't know if you see here, but this is plots of the ratio between CO2 to 1 and CO1 to 0, okay? CO has very low critical densities, okay? So you do a grid of models for different densities and different temperatures. And basically, because the gas is so optically thick, the intensity only depends on the gas temperature. And you see this very nicely, that the ratio of these two lines, they basically will tell you what is the temperature of the gas. So you can use CO basically as a thermometer of the gas, okay? But then you go to another molecule with much higher critical densities, like HCO+. So then the equation of relative transfer will tell you that we are still sensitive to the opacity and we are not sensitive to the gas kinetic temperature, okay, because we are in the subthermal regime. And you see that the line ratio of these two molecules, okay, now has a completely different shape. So basically HCO+ here can be used as a trace of the gas density, okay? So depending on what you want to do, I mean, tracing the density, tracing the temperature, you have to learn how to use different molecules. All right. One important thing is that never forget to cite the people that did the work, okay? So in the equation of statistical equilibrium, you see here things that depends on the spectroscopy of the molecule, so the Einstein coefficients, okay, the B, A, the line frequencies. There are two major web pages, so Cologne CDMS with a lot of experience in molecular spectroscopy. You have also JPL so far, so good. And you also have the collisional rate coefficients that you can find them tabulated in this Leiden database, okay, and also in Paris, okay. So most of the people directly cite the database, okay, but don't forget to go inside and try to really thank the people that actually did the computation, you know, because sometimes, for example, to get the collisional rate coefficient, you may need like 1 hour, well, sorry, 1 year of computation, okay. Very good. So I will skip this. And well, how much time do I have? 20 or something, no? Okay. So is there any question?
Hi, thank you. Great. It's been great so far. I was wondering if you could talk more about masers and where we might see maser emission specifically, like with carbon or CO.
Yeah, maser are, in fact, one guy, Charlie Towns, got the Nobel Prize for the maser emission. So they realized that, well, with paper you can see that populations can be inverted. For this, for a maser, you cannot produce a maser with a 2-level system. You need at least 3 levels, to produce this inversion. So more population in the high energy levels than in the lower energy levels. So masers can be in principle excited by collisions, because it's a dense environment. For example, methanol masers, around massive stars. In other regions like evolved stars, you have SIO masers, but this time the excitation is through the absorption of photons, so it's like pumping excitation. Okay. The incredible thing of the maser is that sometimes you produce some masing emission that the tau is so negative that the amplification factor, so exponential of tau, becomes so huge that these lines can have like thousands of Kelvin in brightness temperature. So they are really a lighthouse to understand. But these are produced in very particular ranges of excitation. So that's why normally masers are produced in, in little spots, around stars or something like this. But it's something that we see masers in methanol, in water, in SIO. Okay. So this is something that happens in nature, in reality. Thank you.
Thank you for the presentation. I have a small question about the CO and HCO plus graphs. So in the HCO plus one, we see that at some point, the right curves, they shift and they become curved. Is there like a limit for like for the line ratios, or we can, yeah, the second one, we see that the curves on the right become too curved. Is there like a limit over which the ratio we cannot determine the?
Well, there is nothing I can provide you like as an answer, because all these curves depends on the exact column density that you put into the system. So it depends on the exact opacity. Okay.
Okay.
So in fact, this is not mine. This is from a student of Antoine Rueff. So I forgot what was the column density he was using. But you can turn your question in the other way around and say, okay, I can only use HCO plus and trace of density in this domain, Okay. But these plots in general will depend on the column density that you put on the molecule. So you have to do like a grid for your average physical and column density in your medium and check this, yes.
Okay, thank you.
Yep.
Sorry, just another question about the maser. Like sometimes you need collision to excite it to achieve this population inversion. But if you have too much collision, you can also collisionally de-excite higher transitions to lower transitions. So how do you know at what critical density you would have?
Yeah, of course, in the limit of high density, you will always have more collisional de-excitation. So this maser emission, I think you were asking, no?
Yeah.
They are producing a narrow range of excitation conditions, okay? That's why we don't see masers everywhere, Okay. So it's true what you say. So normally the masing effect is producing a narrow range of temperature densities and pumping, And so if you find a maser, it's because you are in this particular range that you manage to invert the population.
Is there like a general rule for this, or it's just?
Well, depends on the molecule, on the column density. Some molecules produce the maser emission when the opacities are high, but other molecules produce the maser emission when the opacity is low. So you really have to model the particular source. I mean, the particular molecule. There's no general rule, depends on.
Okay.
Yeah.
Thanks.
Okay. Maybe one more and then we keep going.
There will be no more equations. So okay. I only have like 20 minutes, no?
Okay. I think
so. I will probably not cover all I plan to cover. I'm just going to forget the equations now and go to the fact that we see molecules in the ISM and we see molecules in galaxies. And of course, the reason is where are these molecules coming from and how are they formed? If you're a physician, and you take into account the size of a molecule, meaning the cross-section of a molecule, the typical speeds in a molecular cloud. And then you have this reaction collectional rate that you have to believe me is something like 10 to the minus 11. Even in a dense molecular cloud, that this one density is 10 to the 5. When you make the numbers, you will see that the time for two molecules to collide is like 2 weeks. So if you are a molecule in a molecular cloud, you are really isolated and alone, because you only see a molecule, from time to time. So the chemistry in the ISM has to be slow by definition, and that's why in the previous century, many astrophysicists did not expect molecules to appear in the ISM. In fact, very clever astronomers, physicians like Eddington, he was busy trying to prove general relativity. He will say that it's difficult to admit the existence of molecules in space because once a molecule once a molecule becomes dissociated, there seems no form to join again. Okay, so these people, they were in fact saying something like atoms are physics, but molecules are chemistry. For them, chemistry was like, we are physicians. In the ISM, everything has to follow an equation. And chemistry is too dirt. So molecules should not be there. However, already in the 30s, people, by observing the line of sight towards stars, they detect these broad lines. This is the rotation of a star. But they also detect these narrow features. So narrow means that it has to come from a very quiescent medium, so interstellar clouds. And they started to detect CN and CH. And still many physicians, they say that it is difficult to conclude that these molecules are really coming from the ISM. In fact, from this detection of simple molecules like CN, this time this is in the optical, so these are electronic molecular transitions. If you have different lines, you can work out the excitation temperature of these molecules, And these people, they inferred an excitation temperature of about 3 Kelvin, okay? And this guy here, which is Herzberg, is like the father of molecular spectroscopy. So this is like the Bible of molecular spectroscopy. In the 50s, he wrote, well, we have detected these molecules. They have a rotational temperature of 3 Kelvin, but this has really a very restricted meaning, okay? So in my previous chapter, I talked about when the densities are very low, okay, the molecules, they are not excited by collisions, but they are thermalized to the background radiation. So the background radiation was 3 Kelvin, and what is producing the 3 Kelvin? It's the cosmic background. So in the 50s, they were seeing all these molecules nicely thermalized to the background, the cosmic background. But of course, these people, they didn't know much about cosmology, and they didn't go to these interdisciplinary schools, okay? So they didn't know that there were only theoreticians working in the Big Bang models, okay? But at that time, I think this is the first observational proof of the Big Bang, Of course, the Nobel Prize was given later, 15 years later, to Penzias and Wilson. So yes, molecules exist. They are everywhere. I like this plot because these are molecular spectra of high redshift quasars. I like it because it's observed with the Neumann interferometer, which is not far from here in the French Alps, okay? It's full of molecules, okay? And the nice thing, of course, is that because the molecules are redshifted, their emission are redshifted. So you can observe this complicated frequency domain, 500 gigahertz, in the 3 millimeter band, okay? Because of the redshift, this rest frame emission shifts to frequency that we can easily observe from radio telescopes. So which molecules we detect? You have seen this. Now we have detected more than 300 molecules, okay? 75 of them are in galaxies. So in the last 3 years, I think we have detected almost 100 new molecules. This is because both in GEBES in Spain and in the GBT in the States, we opened the 40 gigahertz domain to observations. Nobody had before observed deeply in the 40 gigahertz domain. And yes, so we are detecting a new molecule like every 1 or 2 months. Okay, so this is increasing. So complexity is everywhere. And in galaxies, because of sensitivity, so far we have detected like 75 molecules. So this H2 is the most abundant, but because of the spectroscopic reasons and excitation requirements, it's not so easy to observe. So we use CO as a proxy. So then I did this. So we see simple hydrides like water. There's water everywhere. And reactive ions like CH+, for example, that is very abundant ISM, but it's very difficult to generate in the Earth because it's so reactive that will react and disappear. Okay? We have the pHs. We have seen this from Emmanuel's talk. Very resistant molecules to ultraviolet radiation. In fact, they absorb ultraviolet photons and then they cascade down, emitting infrared photons that we detect everywhere now with JWST. So in fact, detecting the infrared emission of pHs is somehow detecting star formation because we are converting stellar UV photons into infrared pH emission, okay? And of course, in nearby sources in our galaxy, where we can detect these small hot cores and protostars, we detect increasingly complex organic molecules, perhaps some of them linked to the origin of life, okay, because we are detecting more and more complex organic molecules. And it's amazing that we can detect this complexity. We take into account the famous astronomical periodic table, where the size of the square is proportional to the abundance of the element. So basically, all is hydrogen, helium, very boring molecule, it doesn't like to react much. So it is with this tiny fraction of carbon, nitrogen, and oxygen that we build the chemical complexity that leads to us here in this room, okay? So pretty amazing for me. So why molecules are very important? Well, chemists, they like the ISM because we find really exotic molecules that are difficult to create in Earth laboratories, Sometimes the chemical composition of these molecules in an object changes with time. So if we understand the chemistry, we can use these molecules as clocks, as chemical clocks. But in general, for astrophysics, molecules are very good diagnostics of almost everything you need to know: gas temperature, densities, velocity fields, magnetic field, cosmic rays, okay? And then, as I told you in the beginning, sometimes molecular gas is the only way to cool a system. So, for example, it's the only way that we can really reduce to the Jeans mass and produce gravitational collapse. And in many instances, also molecules are responsible of the cooling of shocks. So you can use molecules for chemistry, and maybe if you don't like much the chemistry, you can use molecules only as astrophysical diagnostics. So people sometimes are very shy to say, no, I'm doing chemistry, my PhD is like, no, I'm sorry, I like to do physics. But the chemistry we have in the ISM is really different compared to the chemistry in labs, okay? So this is the typical conditions in a diffuse interstellar cloud, so a density of 100. In a dense molecular cloud, we have densities of 10 to the 5, And if you compare this with the density that we have in this room, which is something like 10 to the 19, okay, it has nothing to do, okay? In fact, in the best laboratory ultra vacuum chambers, so the regions regions of the space of your chamber, you can reduce the pressure up to 10 to the minus 19 millibars. This ultra vacuum, the best ultra vacuum that we can generate in the Earth, is equivalent to a dense molecular cloud, okay? So the density is so different that it's chemistry at completely different conditions, okay? In addition, the presence of UV photons, X-rays, cosmic rays, turbulence, and magnetic fields means that the chemistry is never in equilibrium, okay? So there is not a temperature you can put in the thermodynamic equations and get the abundances. You really have to solve the chemistry, so the reaction kinetics, okay? And in the ISM, because of the low densities, most of these reactions are molecular, meaning two bodies, okay? In this room, most of the reactions are between 3 molecules. And of course, sometimes because of the low temperatures, all these reactions are not really, they follow very sophisticated and impressive quantum effects. So it's a very peculiar chemistry, okay? So don't be shy to say in my PhD, I do molecules, I do some chemistry. So I will not cover all the possible reactions. So the things that you have to know, at least, it's like even the basic molecule, this is quite funny, H2, the most abundant molecule, is not formed in the gas phase, You need dust grains to form it in the surface of a grain. And then we need fast, in the sense of ISM, fast chemical reactions. So the fastest chemical reactions are those that include ions. Okay, so we need either to ionize them with ultraviolet photons or with cosmic rays. And then in most of these reactions will happen if the reaction is exothermic, okay? If it's a reaction that doesn't need energy, but it's a reaction that will release energy, okay? So these ion molecular reactions are normally exothermic, so this is what we need, okay? And also sometimes to build chemical complexity and to synthesize complex organic molecules, we can use the surface of grains as regions to form molecules. So a molecule AB can, a molecule like AB can form through this reaction, A plus BC, okay? So the reaction rate coefficient will be this K, that depends on temperature. This is the analogous of the inelastic collisional rate coefficient that we were using for the excitation, but this time is the reaction rate coefficient, okay? It has the same units, the units of a cross-section multiplied by a velocity. And a molecule, for example, in the diffuse ISM or in a PDR can be destroyed by photodissociation. So the number of molecules you destroy per second is given by this beta, the rate, okay? So you can set these equations for the formation of AB. only the product of K plus the density of A and density of BC. The destruction of molecule AB will be the product of the dissociation rate multiplied the density of AB. Okay, and you can set these equations. Formation minus destruction is always the same. And in a steady state, so if you wait enough, the density of this molecule that we want to form will have this formula. Okay, the time you need to reach this steady state equilibrium is the inverse of the dissociation rate. So normally molecules are photodissociated and in the ASM quite quickly because these are the rates that we get, okay? Which means that we reach the steady state, or if you want the lifetime of molecules in UV radiated environments is something like about 100 years. This is fast chemistry, okay, for ISM standards. So models include like thousands of reactions, like 5,000 reactions, but there are only a few types of chemical reaction types, you know? Reactions that form bonds, reaction that destroy the bonds, and reaction where you rearrange the bonds. So what we need to do chemical modeling is to know the reaction rate coefficients of this reaction, okay? And this is a complicated business. And again, here we have to collaborate with chemists, okay? So this is the example of this reaction that is forming is OH plus methanol to give methoxin plus water. So it's like inorganic chemistry. So we want to know the reaction rate coefficient as a function of temperature, and you know, chemists with different laboratory methodologies and try to measure this in the lab the best they can. Some other people use quantum numerical methods, you know. And you see that in many cases, there is a negative temperature dependence in many reactions. This means that the reaction, like this here, it goes faster as the temperature decreases. Okay, this is a bit the opposite that happens here in Earth. Then the fridge will be not the best place to store your trash, you know, because here in cold temperatures, the chemistry will be so fast, you know, that you will start to have a smell in the fridge. So this is what happened in the ISM, fast, cold, interstellar chemistry. Molecules can also be photodissociated by UV photons, so the reaction rate is something like this. Again, it's a combination, is the integral of the UV radiation field plus the multiplied by the photodissociation cross-section. So again, you have something that depends on the stellar UV spectrum and something that depends on the molecule, okay, the photodissociation cross-section. So again, you have to collaborate with people that are able to give you this photodissociation cross-section. Okay, so here, so to determine how a molecule is photodissociated, you have both the astrophysics, so what is the interstellar radiation field dissociated in the molecule, and what is the photodissociation cross-section of a given molecule. It's also interesting that we talk about dark clouds, you know, and we say that there is so much dust, so much shielding that there is no UV radiation, but sometimes we have this secondary UV radiation field produced by the cosmic rays. Okay, so cosmic rays will impact these H2 molecules, creating very energetic electrons. Okay, these electrons will collide again with H2, and H2 will be excited to electronically excited states that will try to decay back to the ground by emitting ultraviolet photons. So in the middle of these dark clouds, there is some secondary UV radiation field produced by these cosmic ray interactions. Okay, so this may be important for some chemistry in the surface of the icy grains in these very dark clouds. So astrochemical models, I told you that typical model these days use 5,000 chemical reactions. Of course, we don't know exactly the rates of all these reactions. So we have to either collaborate with people doing experiments, collaborate with people doing the numerical simulations, or try to have an educated guess of these reactions. In our models, what we put is like this kind of Arrhenius fit. Okay, so we tabulate the reaction rates with these parameters A, B, and C. Okay. So here, Tom Miller, previously in Manchester, now I think he's in Belfast. He has the UMIS database. So it's a nice database to check with all the reaction rates. In France, you have Valentin Becklam. We have the KIDA database. So it's very nice because you click into this web page. You ask for the reactants, you know, H2 plus water, and you have the reaction rates and some information about the literature, so about the people that compute these reaction rates. And the photodissociation rates, I think one of the best databases is the one of Evin van der Hoek. Okay, also they tabulate the photodissociation rates and the photoionization rates for different molecules. So what do we do in chemical models? It's a bit like the radiative transfer and excitation. So you have to set the equation for the formation of a molecule X. This molecule then can be destroyed by reacting with other molecule. It can be destroyed by being photodissociated. A molecule can also form the surface of a grain, okay, as an ice, and they can photodissolve or thermally evaporate. So basically, in these models, we have to put all the reactions that form and destroy a molecule with some conservation laws. So for example, the number of carbon atoms cannot change in the model simulation. The number of carbon atoms has to be carbon plus carbon plus CO and so on. The system has to be neutral normally, so the charge will be the electrons equal to the number of positive ions that you have in the system. So the ideal model, you have to, we like to see the emission coming from a molecular cloud. So we have the input radiation field, what will dissociate molecules, okay? We need the temperature because the temperatures will define the velocity of the chemical reaction. So to get the temperatures, we have to do the thermal balance, so heating equal cooling, and then you iterate, until you reach a good solution. You never have to trust so much models, because these are complicated models. Reaction rates are normally known with an uncertainty value. Okay, so you have to be very picky and don't trust your chemical models within a factor of 2 or to 10. Okay, because these are very complicated systems to model. So some of the public models that you can use if you are studying an environment that is dominated by far ultraviolet radiation, so diffuse gas, a PDR, you can download the PDR code, the Midon PDR code, which is very sophisticated. Okay, you can download the Fortran code and run it in your laptop. It does almost everything, so the UV radiative transfer, the heating and the cooling, the chemistry and the molecular excitation. Okay, so basically you can use these kind of models to predict which is the UV radiation field and the pressure of your system. Okay. Yeah, I want to skip this. So you can install the code and run it in your laptop, or now there is a web page in the Paris Observatory that they have run many models for you with standard physical conditions, and you can click this, put your favorite physical conditions, density or gas pressure or UV radiation field, and they will generate plots of different tracers, C plus divided by O1, CO emission. So it's easy to quickly compare to your models. Although if you really want to do something for publication, I will always try to run a model for the dust properties, gas densities, and so on of your particular source. So in this database, in this web page of the Observatoire de Paris, soon they will also have shock models. Okay, so if you are studying an outflow, galactic outflow, a protostellar outflow, they will also collect the output of many shock models. There is an American counterpart, the PDR toolbox. I don't know if we have to pay already in Europe to use this code. So this is by Mark Wolfire, Mark Pound. Same concept. You have diagnostic plots of a PDR. Okay, I think the code itself is not public, but you can use it to generate nice, line ratio plots and try to constrain G naught and density and so on. But if you are observing the ionized gas, okay, H2 region, photoionized gas, where most of the hydrogen is ionized, then you cannot use these PDR models, okay? Then you need to use a photoionization model, and the most famous and widely used is the Cloudy by Gary Ferland, okay, which is also, you can download it. And now here you can get, well, it does almost similar things, heating, cooling, ionization balance, and so on. And with this, you can retrieve the number of ionizing photons, the ionization parameter, the electron pressure, and so on. Of course, there are other PDR, shock, and H2 region models that I have not included this, so apologize if you have your favorite one. So just to conclude, this is what interstellar chemistry makes. Okay, so in the diffuse gas, we have molecules, low density, warm gas temperatures. The gas is heated by far ultraviolet radiation, okay? And the gas is ionized by these cosmic ray photons also. So here in these environments, we see the beginning of the interstellar chemistry. So simple molecules, simple light hydrides, OH plus, CH plus, and so on. In the interior of dark clouds, we don't have much ultraviolet radiation. So we have high densities, cold gas, and the only ionization we have is cosmic ray ionization. So temperatures are so low that very volatile molecules like water, for example, start to freeze out and disappear for the gas phase, so start to build layers and layers of ices, okay? And this triggers the formation of other specific molecules, like deuterated molecules, so molecules that have deuterium atoms. In the opposite direction, in hot core, so the material that was, imagine that you have the cold gas and these thick layers of interstellar ices, and suddenly a star is formed and hits the environment. So all the chemical complexity that was in the ices now is evaporated back to the gas phase. So here are the regions that we see complex organic molecules like methanol and so on. Outflows and shocks, this is high temperature environment. So the temperatures are so high, and sometimes the energy in the shocks are so high that you destroy the grains. So that's why you see molecules like silicon oxide. And temperatures are so high that you activate not only the exothermic reaction, but also the endothermic reaction. So for example, you form a lot of water and OH. These are typical traces of galactic outflows. PDR, so regions dominated where the chemistry and the heating is dominated by far ultraviolet photons. Very typical, you see a very strong emission from pHs and H2. So this is telling you that you have ultraviolet photons, and we have also reactive ions. And in both stars, these are interesting AGB stars because they are the factories of dust grains. Okay, so before you form the dust grains, the seeds of these dust grains are still in the gas phase. So this is one of the few environments where people detect in the gas phase molecules with very refractory elements like titanium, silicon carbide, etc. Very good. So we are coming to the end. Thanks God. Take home messages. So the ISM is a very important and beautiful component of galaxies. You know this. The ISM is slowly converted into stars, and as they die, the stars return enriched matter to the ISM. UV, cosmic rays, and shock hit the ISM, so that's why the stars and the ISM are tightly coupled. There are fascinating physical and chemical physical processes that lead to the physical conditions that we see and that the spectra that we observe. So it's always good to collaborate with the people that really know how to compute the cross-section and the rates of these microphysical processes. There are new developments in the field, in particular the role of magnetic field and turbulence. So there are more and more sophisticated MHD simulation. There is a bright future. I think still we have very nice telescopes operating now. And don't forget never to be now, these days, a multi-wavelength astronomer, okay? Don't focus in your CO2 to 1 transition. I mean, there are probably other lines, other molecules, other waves that can help you. So thank you very much.
Thank you, Javier. Are there questions?
Very good, very good. It's so late.
You're all, yeah, maybe you're all tired.
You can ask me during, I mean, tomorrow.
You'll be around.
I will be around and awake.
Okay. Yeah.
Hi. Thank you for this nice talk. You spoke about the ions in the PDR regions and in photo processes. Do you have some ions ratio which could indicate properties of the ionization in these regions or not?
I mean, ions are very abundant in PDRs because, for example, C+ is ionized. So as soon as it reacts with H2, you start to have CH+. Okay. There are particular molecules that we call reactive ions. So ions, are, in addition to be ions, they are very reactive. So as soon as they are formed, they collide with something and they disappear. So these reactive ions, for example, HOC+, CO+, these ions, we only see them in PDRs or in starburst galaxies, if you want, okay? So if you detect one of these ions, you are sure that you are in a UV-radiated environment, okay? But you were asking for the ionization, no? Trace of the ionization?
No, and also typical ratios which indicate the conditions in these regions. Like, okay, you gave HOC+.
Yeah, well, for PDRs, classical, well, you can use, depends on what you have, you can use H2 now with the JWST, it's very useful, Back in the days when we had Sophia and Herschel, you could do a lot of PDR modeling with the C+ and O1 ratios, This we cannot do it now, but if you're observing a high redshift galaxy, you can still observe with ALMA. Okay.
Are there any other? Is there? Yeah. Okay. Simon.
Well, just a bit of a follow-up. What you can also do is you can use the C+ and the N2 optical lines, because the N2 only traces the H2 region, the C+ traces the H2 region and the PDR. So the ratio of those two tells you kind of how much C+ you're seeing from the H2 region versus the PDR.
You see the optical ones?
The optical N2 line.
Okay.
I mean, it's also got a fine structure line, but yeah.
More
less
excited.
accessible.
No, I really, in this context of PDRs, you know, and traces of gas at large scales, I think we need something like PRIMA in the fine thread, you know, because we don't have access right now to the main coolants of the gas, you know, so we don't have access to the peak of the dust emission. We don't have access to the more important cooling. I think this is dramatic, you know, but it's hard because it's a very complicated part of the electromagnetic spectrum, because you need to go to space, you know, so what this means expensive. So I think the future, I don't know if it's so bright in the fine thread, yes.
Yeah, I also have a question.
So I just had a question about one of your last slides when you showed the planetary nebula, and you say that we detect, titanium oxide, SiC2, and you say that those were the seeds for dust formation, but those don't look in terms of composition like the dust we know. So is it really because they could be the seeds to grow normal silicates, or just because those are the only molecules that we can easily detect?
Well, to be honest, I'm not an expert in this field. Yeah, I think with ALMA, when you detect these molecules really close to the photosphere. So in this case, you haven't still formed the dust grains. But yeah, I'm not an expert, but I don't know.
The last question. It concerns these PDR models, which, if I understand correctly, reproduce this scheme of the 70s, where you have these slabs.
Sandwich.
Yeah, exactly. But then as you mentioned, the ISM is clearly a dynamical system and so on. So what's the prospect for chemical models to include the dynamical complexity, actually? I mean, it's very difficult, I guess.
Probably it's the other way around. So these dynamical models, how they will include chemistry, you know? This is probably the key. I mean, in dense PDR environments, you know, the equilibrium.
Yeah, I mean, in this case, this kind of sandwich.
In a dense environment, this chemistry is fast, you know, so it's okay to do steady state models, you know, because the equilibrium time to form H2 is like 10 to the 9 divided by the density. So you really need these dynamics to understand the diffuse material, you know, because then a steady state doesn't give you the correct H2 abundance, okay? So I think the future for these people doing these ISM simulations really to include more and more description of the chemistry, which is time consuming, you know. A PDR model run with the medium PDR code takes like 10 hours in a laptop, you know, for one point.
So as someone who has recently started working with the chemical network in the simulation, Simon has much more experience, but I was wondering, how do you close the loop and you go back to observables? Like you have done a simulation that includes some chemistry, not all chemistry, and you have your new abundances in dynamical environment. Yeah, probably
what they do, I think
you need to go back and check or what.
Well, they have these sophisticated dynamical simulations, and then you can do the chemistry in what they call the post-processing. No? So you extract a given area with different temperature and density, and there you compute the chemistry outside.
No, I mean, even if you do it on the fly, in the end, I have a galaxy that then at each cell, I know velocity, and I know like, I don't know, 100 chemical species. So how do which one of these methods, as you have mentioned, is the appropriate method to go back and see what the line ratio would be from that simulated environment.
Well, I have problems to really understand light ratio in a nearby source. So in a galaxy, already the key point is the average. You are averaging many different things. Okay.
Oh,
But you must be dominant. You can be dominated by.
Related the question properly. So if I want an observable, like I have all the simulation, all the simulation, I have velocity, density, temperature, electron density, well, carbon, ionized carbon, whatever, like collision ion. I have the radiation field. How do I know what would I see? Which of these codes will tell me what I would see? I would redo the radiative transfer with all this like information given.
Well, I think first you have to know your galaxy. So if it's a star-forming galaxy, starburst like M82, then you can use the PDR models as an average of what you see. And I'm sure it would do a great job. But if you use a PDR for an AGN, it doesn't make sense. So you have to do, yes, there is, Simon.
Well, I mean, to give a more concrete answer to your question, you take all of that data and you put it into a 3D radiative transfer code. And you hope that LVG is going to be good enough for what you want to do, because the more exact methods you can't afford to do in 3D for those types of calculations. I mean, Lime, I think, scales up to about 10 to the 4 or 10 to the 5 cells. But I mean, compared to what we run within Galaxy simulations, this is still tiny. And things like RedMC3D or Polaris that can cope with very large simulations, they're just doing LVG because you can't afford to do non-local. Yeah. Yeah, the Polaris will absolutely do that. You can take the data, plug it into Polaris and solve it.
Yep. So maybe a final remark, comment?
Just to say, but you're talking about two different things. This is a radiative transfer, so assumes abundances. Okay, so all these codes that Simon is mentioning is assuming the abundance, like is taken for granted. While all the stuff that Javier has talked about in this latest part, you are simulating the chemistry. So it's the part before the radiative transfer where you say, how can you make these abundances or column densities that you feeding into the radiative transfer? And you can, of course, not do that and just use column densities as known, which is fine in some cases, but in some cases you're putting in things that would never happen in chemistry, but the radiative transfer code takes them at face value and says, okay, you gave me this column density for this gas density and for this temperature and this radiation field, and I'm taking it at a face value. But then the chemist will tell you, you can never have this amount of HCO plus with this gas density, this temperature, but the transfer code doesn't know this. Won't know this because it's not doing chemistry. So just to differentiate, these are two different things, what the codes that Javier is talking about in this last part and the codes that Simon is telling you that you can use.
Well, the Meudon PDR code also predicts at the end the observed spectrum. You know,
exactly,
it's a little radiative transfer.
But it does the chemistry first. The codes that Simon was talking about, these are just radiative transfer codes.
Yeah, but it's 3D, so it really captures the dynamics. So there is no perfect.
The chemistry.
Yeah. The only problem is, I mean, for galaxies, you have emission from average regions, you know. So the only thing you can do is you can use a model, and the model will tell you the average physical conditions in this beam. Is there any position in the galaxy with these properties? I don't know, but this is the average, you know, and you have to push this because you have to go from photometry to spectroscopy, and line ratios, even average in kiloparsecs scale, will tell you something. I mean, the spectrum of a galaxy of an AGN is completely different to the spectrum of a starburst. So,
anyways, I think this is a nice point to break. I think it shows that, you know, bridges between dynamics and chemistry are essential, even modeling. So let's thank Javier again for today.